So yeah, after 1 month, I tried to do it again. So hopefully everything goes well now. So today what we are going to talk about is about some calculations that we have done recently in Graphene. And these are the simulations of a transient absorption type of experiment that we could do, but with attosecond pulses. So before really starting with the main part of the talk, let me introduce some couple of slides just to talk about why it's so special attosecond science. Okay, this is not, here we are. So if we think about, can you see well my screen? I mean, I don't know if I should remove this maybe. There we are.
You're fine.
So if we think about the order of magnitudes, if we compare, for example, 1 second with the age of the universe, this is around 10 to the 18 seconds. Now we go down, if we compare the 1 second, but for example, with how much time it will take an electron that it will orbit an atom, that it will be several attoseconds. So that is in the order of 10 to the minus 18 seconds. You see that the order of magnitudes is similar. It's just in the microscopic microscopic way. So what is really fascinating is that nowadays we have really the technology to produce pulses that they can be as short as several attoseconds. So just to give a brief explanation of how these are produced and more or less what are the parameters. The typical way is to use high harmonic generation. So what we do is to focus an intense infrared laser or mid-infrared laser in a gas phase jet. And what this is going to produce is a strong nonlinear perturbative regime in which is going to emit harmonics. And these harmonics are going to have frequencies that are very high. So this is a little bit the scheme that usually people, they explain this phenomenon of high harmonic generation. Is first, the laser is intense enough to bend the atomic potential, so the electron wave packet can be ionized. And this electron wave packet is going to be driven back and forth by the same infrared pulse. And at some point, it's going to get close to the atom, and there is a certain probability that it will recombine. And if this happens, this kinetic energy that the electron wave packet is gaining in the continuum can be released in the form of a photon. So this is how we produce very high frequency photons. And with this technique, one can really produce the attosecond pulses, which I'm not going to get into details here. So if we think about the first attosecond pulse that was produced with this technique, it was around 2001. And the first experiment, there were photon energies around 90 eVs and pulse length around 600 attosecond pulses. And we look at nowadays experiments that there have been a huge improvement in the mid-infrared technology. So we see that these pulses, they are going down in pulse length. So for example, this one is in 2019, they reported 40 attosecond, while the photon energies, they are also going up. So in this particular case, for example, they were reaching almost like 200 eV. And I will show in some slides later that we can really reach the suffix range. So we can reach the 500 eV. So why is so useful? What we can do with these pulses? So we have the technology to really make snapshots of the dynamics. One of the things that we can do is to study electron dynamics, and not only that, but also electron correlations. And actually, this has been a very vast field of research especially in atomic and molecular physics. However, here what we are going to do is to really focus in condensed matter. But before going there, just let me explain a little bit of the different schemes, because one thing is that really produce the technology to really have attosecond pulses. Another thing is how we can really interpret the data and how we can obtain information about the electron dynamics. So there have been two successful schemes in that they are based in photoemission. One is what is called optical streaking, another one Graphene. So in optical streaking, what happens is that at the second pulse, it will ionize one electron from the system, and then at the same time, it's going to be a strong laser that is going to dress the continuum. So we look at the photoemission spectra. So it's going to look like, depending on the pan-probe delay between the laser and the attosecond pulse, we are going to observe this streak pattern. That is basically the line of the photoemission that there is suffering an energy shift due to the laser. So with that, you can kind of know as a reference time where you want. Another way is to use Rabbit. It's very similar. Also, you ionize an electron from the system, but now you are in a regime in which you take several harmonics, and then what you observe is like there are interference between the different harmonics, and this interference, they not only give you information about the photoionization yield, but also the phase, and this can also be correlated with the dynamics of the system. Now, the one that we are going to be explaining today is transient absorption that you are probably familiar with. But let me explain a little bit the main difference with what we do in synchrotron. So here the laser pulse is going to go from a branch, and then in this line is going to be focused in the first gas phase, and it's going to produce the harmonics that it will produce our attosecond pulse. In the other line, with the same laser, but it has been split, it's going now to go directly to the target that we want to study. So in one side, we have the attosecond pulse, in another one, the infrared pulse that we use to generate the same attosecond pulse. And it has clear advantages because then these two lines are synchronized, and it's easy or at least it's possible to change the time delay between the two pulses with very good precision. And then these two, they are going to be focused on the second target, that it can be a gas phase, like in this scheme that I'm going to show, but it can be also a solid. So this is what I'm going to show later. So after the attosecond pulse goes through the system, basically what we are going to do is to measure the spectrometer. So we have here an spectrometer, and then what we can do is to just send only the attosecond pulse, take the spectrometer, we analyze well, we characterize well how is the pulse. These pulses are very robust, so during hours, pulse will be the same. Once that we know the structure of the pulse and the spectrum of the pulse, then we switch on the laser, and for different time delays, we observe the changes in the absorption. So we take the difference of these changes as we are plotting here. This is the changes. So this axis is energy, and what we are plotting is difference of absorption. And here in this axis is the time delay between pump and probe. And this is, for example, for helium atom, and you see that we can see these patterns due to this measurement that is what we call attosecond transient absorption. From now on, I will just call it atom. Now, one of the advantages that this scheme has compared with the ones that are based on photoemission is that they have a high temporal and energy resolution. Because if you here, for example, you use a very short attosecond pulse, it means that if you are doing photoemission, you're broadening in the continuum, the energy broadening will be larger, and then it's going to compromise also the energy resolution. So in this particular scheme, this doesn't happen. So this is one of the nice features of atom. So before continuing and going into the condensed matter part, let me explain one of the nice features that we have realized around 2013, that is the following. So now, maybe I didn't emphasize so well, but here what we measure is really the bandwidth of the pulse. So the pulse is short enough and it has a big bandwidth, and it goes through the system. So we can only see the absorption that is inside the bandwidth of the pulse. And you see that these energies, it means that this is the broadening of the pulse. Okay. So in this experiment, that is also in helium, you see that, for example, here it will be an attosecond pulse that goes through helium, and then we are observing at the absorption that they go from 64 to 65.4 eV. But the pulse, the attosecond pulse, is broad enough that really covers all these energy windows. And if we measure just the attosecond pulse going through the medium, we'll see this type of peaks in the absorption. And these funny looking peaks is what we call fan of resonance. And usually these resonance, they are explained as the following. So in helium, they are like resonance where when we excite, this resonance also is coupled to the continuum. And this coupling is what it can really make going from something that we know that is a Lorentzian peak to something that is what we call a Fano peak. And this is what we are observing here. And typically, we have always thought about Fano resonance in the frequency domain. Now I'm going to change a little bit the gears, and I'm going to go to a time domain. So we know we go now to the time domain, and if we think on a simple excitation, then I'm going to have a dipole that it will oscillate like this, and it will have a particular lifetime. So it will be damping. And then we do the Fourier transform to calculate the absorption that is related with the polarization of the medium. So we'll see the typical Fano profile. Now, when we introduce this coupling, now one can think this coupling as in the time domain, we introduce a particular phase in time. And this particular phase is what is going to give rise when we do a Fourier transform to this Fano-looking peak. Now, what they realized in this experiment is the following. So imagine that right after the excitation, and I have my dipole that is oscillating. So during this oscillation, right after, I'm going to send an infrared pulse. So the attosecond pulse already went through the system, and now it's arriving the infrared pulse. Another infrared pulse, what it's going to do is to introduce an optical star shift in the resonant state, and it's going also to introduce a shift in time. And if this is true, what happens is that we have a similar effect than here. I mean, we can recover something that before it was doing the coupling with the continuum, but now we can just induce it by the laser. And what they did is the following. So they switch on the laser, and then they observe how these line shapes, they are changing to these ones that you have in B. So these are the experiment, and you see that they go from something that it looks like Fano peaks to something that it looks like Lorentzian peaks. So again, this is Fano, but we can also think Fano in such a the Fano resonance is just really very similar to what we are used to think about the core excited states. So this is how I'm going to generalize it later. And then I will come back to this slide probably. So keep in mind this. But when we have a condensed matter system, now when we create an electron, this electron is bound, this electron hole pair is bound. But in the case of the condensed matter, it will be having an exciton that it will be able to move along the bands. So this optical star shifting will be much more complex because we will need to take into account this exciton dynamics. But it will really be imprinted in what we are going to observe in the absorption. So it will change the line shape of the absorption lines. So let's continue. So ATA has been already implemented in several applications to study solids. So here, for example, you have a paper of 2014 in silicon. Silicon is an insulator, have a big band. So what they do is to really go with a very intense laser. So they bend a lot the lattice, and they're able to promote electrons into the conduction band. And what they study with ATA is that they were able to grab this kinetic plot. And you see that the resolution is usually in the attosecond pulse. I mean, this carrier injection is just happened in 8 femtoseconds, and we have this really nice resolution. So perhaps here I should emphasize that we are investigating the physics right after excitation. So when the electronic response is the dominating one, so right after here. Of course, you know, we let the system evolve. At some point, it will couple with the lattice, and then we are going to have a lattice response. But this type of experiment, what we are concerned is about this first electronic response. So if we look at the literature, there have been already several studies, experimental studies, and it goes from semi-metals to semiconductors, insulators, bulk materials, quantum materials, very thin materials. So ATA is really possible to do it even, you know, in very exotic systems. Just before going into the slides of questions, just let me say that recently with mid-infrared pulses, they are able to produce attosecond pulses that if we look at the spectrum, it would look like this. This is a measurement. It was taken in the laboratory of James Bigger at ICFO. So you can see that we are really able to reach the 500 dB. Maybe we don't have still too many photons to do time resolved experiments here, but definitely we can do it in the nitrogen KH or in the carbon KH. And also there are other interesting shell edge that we can study with these attosecond pulses. And of course, if we have access to the carbon KH, one of the first things that it triggers is that we can study graphene-based materials. And this is what I'm going to show, a freestanding graphene calculations. But before that, just let's stop for questions.
I have a question. So yes. When you use the pump laser, I'm thinking of the helium experiment to begin with. And so the system is excited, it's ringing, what have you. And then you do photo absorption. When I compare to the ground state photo absorption, is it still purely a dipole selection rule?
You are talking about this helium case, right?
For example, yeah.
Yes. So this is dipole allowed. I mean, you don't really need to have a multi-photon excitation here, which you could have it, but the attosecond pulse could come first and not overlap with the laser, and then it comes the laser. So the laser mainly what it's doing is creating an optical star shift.
Mm-hmm. Right, but so does that give you access to states that you wouldn't have otherwise, or is it just changing the response function to strictly dipole allowed states?
I mean, you could, yeah, that's a good question. I mean, you could go to other states, but here's more about you don't go to another state. You just you stay in the same. You stay in the same state, but you just introduce this dynamical phase, and this is what it changed the line shape of the absorption.
Okay, I understand. The reason I'm asking, if you go to the slide where you show the many edges that are available in your energy window,
this one,
right? The broad peak with the vertical lines, where you talk about, yeah, that one is there's actually, you were only talking about L, but of course there's also for heavier elements M and N and so on. But for the most part, those are only spectroscopically interesting if you go outside the dipole selection rule, such as with X-ray Raman scattering. And so that's why I was wondering, is it possible that you have even more edges that could be spectroscopically interesting, specifically in a pumped situation? And so hence the question about dipole selection. And if it's not obvious, that's okay.
No, no. I mean, what you can do, I mean, if you want to have X-ray Raman, I guess that you need a lot of intensity in your X-ray pulse.
I'm not expecting you to do X-ray Raman here. My question is just when you do a pump probe experiment, attosecond, is it possible that you have selection rules other than dipole, or effectively that you have access to states that you would not have had in the absence of the pump?
Yes, yes. I mean, if you have the pump that is the infrared pulse, you have the infrared pulse there. Yeah, you can have multiphoton. Yeah, absolutely.
Okay. Okay. All right. Very good.
Yeah, I
thank
mean,
you.
if that one is very strong. I mean, if you crank it up, the intensity,
see.
you can have
see.
a big fauna of states. Yeah.
I understand. Okay. Thank you. Matthew, you have a question?
Yeah, so I was wondering about the effect of the spectral analysis that you do at the output on the time resolution, because of course you have the uncertainty principle. So that means, yeah, that. And it reminds me a bit of doing wavelet transforms on XAFS data, where you have a tension between R resolution and K resolution.
Yeah, you know, this is this actually a thing that has been already implemented in synchrotrons, and they call this dispersive absorption. Maybe someone knows better than me. But I found this technique that it was already implemented in synchrotrons. So mainly what you do is just you know, you don't use the monochromator. You just detect the whole spectrum.
Yeah, but
right?
I'm wondering what since you're energy selecting the output, that surely must produce a broadening in time.
Yeah. So the pulse, I mean, let's say that you compress the pulse, right? The shortening of the pulse is going to broaden your energy windows, and then your energy resolution will be compromised mainly for the technical specs of the spectrometer. And then your time resolution is kind of given by the time delay. But of course, I mean, it's kind of tricky, right? Because you have seen also that that also if the system is still, you can have a very an attosecond impulse here, but then you have a a particular response of the system. So if the system, you know, is still interacting with the laser that is coming later, it will also affect.
So I think maybe where Matthew is going is with this figure you have here for the doubly excited helium, it looks like your energy resolution is, I don't know, 0.1 or 0.05 EVs or something like that.
Right.
And so if I throw Planck's constant at that, I would say, oh, that's 10 femtoseconds or 20 femtoseconds. I can't do that in my head because I'm old. And so we're curious, where is that giving time broadening? Is it an uncertainty in the time delay, or somewhere else? How does that influence the ability of the experiment to work?
I think the resolution is given for the spectrometer. If you compress your impulse pulse, the only thing is that you broaden the spectrum, right? Mm-hmm. But you don't compromise your resolution. The resolution is given by the spectrometer. And your time resolution is, I guess, that is given by the time delay between the pump and the probe.
Yeah, I think that's the answer. Is that that's an external experimentally set thing. It's not something you're trying to infer at the same time. So yeah, I don't think there's a mutual constraint here, but maybe that's something we can talk about again later.
Yeah.
Not seeing any other questions. You should continue, Antonio.
Okay. Okay, so this is a little bit the different research line that we are doing in our group. And today, mainly what I'm going to talk is about attosecond X-ray spectroscopy in graphene. And for that also, I will need to talk just a little bit about, the numerical model that we are developing to calculate this absorption. So this has been in collaboration with our collaborator in Universidad Salamanca, Luis Plaja, and the people that is mainly involved is Giovanni Sistaro, that is PhD student with us, Michal Malakov, that is postdoc, and Fernando Martin. So what we do is the following. So we treat the system and we evolve it, but what we evolve is actually the reduced density matrix. So we derive the equation for the evolution of the density matrix. What we are going to obtain is some differential equations that they look like this. And I'm going to go quite fast, but what we do is mainly to solve these equations. And for that, what we need to do is to discretize our grid. So we work in the reciprocal space because it's easier for us and to interpret energy dispersion and so on. So what we do is to discretize the grid. And then we have to take into account the pump and the probe. So what we do is to select areas where we are going to call what are conduction bands and valence band. And these ones that are going to be interacting with the infrared laser. Infrared laser can promote interband transitions, but also intraband. So the laser can also produce the electron move along the reciprocal space. And on the other side, we are going to have the probe that is going to be this attosecond X-ray pulse that is going to select these core bands. And here in the middle, it's going to be some bands that we are going to neglect for the dynamics just to reduce the computing time. And then these ones are going to be able to couple to the conduction on the bands. And this is mainly how it works. So in order to compute this, so we have to parallelize because these are computationally costly. And what we need to do is to mainly calculate the energy dispersion of the material, the direct connections on the material. We introduce in there, and we can calculate these electron densities. So how the system is evolving. So if we do this, how we calculate the attosecond absorption. So it's easy. Once that we have this information about the electron density, we can compute, for example, what is the polarization of the medium. For that, the only thing that we need to do is to calculate, multiply this by the direct connection. This is kind of a dipole. So this will give us the dipole of the system in time. And with this, we can mainly calculate the absorption. Note that here it's kind of like in the experiment. We send the attosecond pulse, for example, and it's starting to start the dynamics. And after the dynamics, we do the Fourier transform here, right? But this pulse doesn't need to be monochromatic or weak. I mean, we can introduce any pulse that we want. Because this is computing time, and then this will give us directly the absorption for a range of omega, where this omega is going to be constrained where I have the bandwidth of the pulse mainly. This is the Fourier transform of the electric field of the pulse. So this is mainly how we are calculating the absorption. So we did a first calculation for graphene. So what we did is the following. We consider a pump probe experiment in which we're going to have a 3-cycle pulse of infrared pulse of 3 nanometers. This is feasible nowadays. And an X-ray photon energy of 280 eVs, which is also feasible. And these two, what they are going to do is the infrared mainly is going to produce dynamics of the electron carriers around the Dirac points. So here we had the valence band and the conduction band, and the valence band of graphene. And then we introduced two more bands that they are accounting for the 1s orbital, that is the 1s electron that is able to go into the conduction band, right? So we have 2 carbons in the unit cell of graphene. So that means that we need to include here 2 bands. Because this 1s is going to be not forming any chemical bond, they are going to be flat bands mainly. So we did the simulations. First, we introduced only the attosecond pulse. We send to the system the attosecond pulse, and then we calculate the absorption. And what we obtain is what is in gray. So this is laser off. And then what we do is now introduce the infrared laser. And now this is just for time delay 0. And then I will show what happened when we move the time delay. But for time delay 0, we see that the line shape of the spectrum is changing, Mainly is they're like gathering around these points, right? That corresponds to K prime, that are these points that are the Dirac points, that are degenerates, the M points that are these ones, that are the arch between the K and K prime points, and then the gamma points that are the ones that are on the top of the, they have the most energy. So if we take the difference, we get the transient absorption for a particular time delay, and we see that really the main difference are really focused on, they're really focused in these points, which they have in common that there are Van Hoff singularities. So now what we can do is to do the same, but now in our calculation, we do the same that in the experiment, we change the time delay between the two pulses. Remember that here we work in the time domain, so different time delay means that we just introduce different time, a different combination of pulses in time, and we'll get this spectrum. And then we get the atoms. So this will be, this is for time delay 0 that I was showing before, and then changing the time delay, we get this spectrum. And again, we can see like 3 big features that one that is localized in the K points and the other ones in the M and gamma. Now note that the ones that are localized in gamma and M, they're a little bit separate compared with the ones, they're a little bit different compared with the one in K. So in K, it seems that, you know, the changes in absorption, it will be there for longer time delays. However, the other ones, they look like they're like disappearing quite fast, right? So they are not quite the same. So at the beginning, we were wondering why this is happening. Also, another interesting feature is that gamma is kind of far from the K point. So this is like 90 beam. We are pumping with a 3 micron laser. So it's very difficult when intensity we're using to actually populate this point. Actually, we were not populating because we can see the electron density, and we can see that we are really not populating this gamma point. So how, you know, how we are introducing these changes in the absorption. So this is going to be a little bit related to what I started to show in this experiment of helium. But before going there, maybe we explain why these changes in the K around the K point are happening. These are the ones that are easy to explain. So if you look at these changes, what happens is that if it's blue, it means that the absorption is decreasing. So what is happening is that the infrared is populating electron carriers up. So now states that they were unoccupied and were able to occupy, now the core electron cannot really occupy this for Pauli exclusion. So the absorption is going to be decreased. So this is what we are noticing here in the blue line. Similarly, the same for the balance. So the red means that the absorption increased. So we have more holes that are created. And then it means that they are disoccupied, and then the core electron can occupy now these states that they were before occupied. So the absorption increase. One of the nice things of these calculations that it would be very nice to be able to really have this resolution in the experiment is to really observe this interference. So this interference that we observe here in the absorption are real, and it's because, you know, we have the electron wave packet that is coming in this 3-cycle infrared pulse, is populating up the conduction and then come back, and then there is another pathway that they will interfere. So what we are really observing here are quantum interference of this quantum electron wave packet that is populating in a periodic way the conduction band. And we can also understand that after the infrared is gone, we have a particular carriers that they will be just excited in the conduction band, and they will stay there. So mainly we have this pattern. So the other pattern is a little bit more difficult to explain, and then we have to go back to what I was explaining before with the fan of resonance. So what we did is the following: is to create a similar model, but now for condensed matter. So it's taking two bound states. Here, what we are going to take is the core electron that is going to go up to the conduction band. And now this core electron is the one that is going to be feeling the presence of the infrared pulse. So in this case, as Jerry was mentioning before, because we have a simple two-band models, we are not considering other excitations. But if we have more bands, of course, we'll need to consider it. But just to grab the ideas why the changes in the absorption are happening is enough to consider this simple two-band system. So we treat only the conduction band, and so the core electron, mainly what it can do, the promoted core electron, is to oscillate. As soon as it has time because there is a lifetime to take into account, that is the core hole decay. So if we look at the dipole in a phenomenological way, we can write it like this, right? It's going to be something that is going to oscillate. It's going to be given by this imaginary exponential plus complex conjugate. It's going to be the difference between the difference of the energy times and another term that is going to take into account the damping of the core hole. This if I don't do anything. So if I switch on the laser, now this electron can move around. Before it was just oscillating as a dipole. It's a vertical excitation with the attosecond pulse, and that's all. But now with the infrared pulse, this electron can really move along the conduction band, and then it's going to acquire a phase. And this is what is nice. This phase is a little bit, maybe it's a little bit difficult to express, but what is important is there are two terms. One that depends on the energy dispersion. So this is the K in which the electron has been excited. And then this is the vector potential of the infrared pulse. So the vector potential mainly is oscillating this electron. And this difference is accumulating, that is related to the local energy dispersion, is going to accumulate a phase. And similarly, one term that it depends on the barrier structure. So if you see, this is very similar to what we had before in helium, because now I am introducing a phase in time that it can change the line shape of the absorption line. And of course, remember that here is for a particular K, but what we measure is really the sum over all our BU in zones. So we have to sum over all the reciprocal space, and then we obtain the dipole in time of the system. Very quickly, the barrier structure for a two-band model can be easily described with two angles that the depends on these parameters that are given by the Hamiltonian that you are considering. So these two angles is something that we can calculate easily. And in this particular case, that is a multi-banding model of two bands is easy to calculate. So I'm going to stop here for more questions.
All right, well, we wait to see if there's questions in the chat. I have one for you. So you've been specifically looking at graphene, and you're able to see, for example, substantial changes near the Fermi level. Two questions about that. First one is, I understand that, I know your interest here is about the time window when the infrared and the attosecond is overlapping, so that you get this this driving of the excited electron and whatnot. But you have this persistent excitation near the Fermi level, at least on the scale of femtoseconds. Can you say something about the apparent electronic temperature? So is this a warm dense matter experiment, for example?
No, I didn't consider here the temperature distribution. So that's a really good point. At this point, I was just trying to understand, with a very simple model, what is happening, right, in graphene on these attosecond time scales.
Got it. Okay.
Yes, but we didn't implement it still. We didn't do the calculation with temperature distribution.
Got it. Okay. Second question is, so here, these different points in the band structure give you different ways to investigate the interference between the effect of essentially the simultaneous pulses is not interference between them. You've shown how they independently come into the phase shift. Are you learning something new specifically about graphene? And are there other layered systems where you think the attosecond spectroscopy could unravel some of the interesting things that are happening?
Yeah, this is going to be a little bit the outlook of my talk. So
Okay.
we believe that yes, but you know, from the experimental point of view, I guess that is challenging. But we believe that yes. I mean, long story short, just to give a flavor of the main point, you're able to move this electron that is going to acquire a phase, right? And maybe this phase is going to give you some information about the energy dispersion, but also about the baric structure. And this is something that nowadays is interesting for the modern materials. So, if, for example, you have a particular Berry curvature at some part of the reciprocal space or not. So these are a little bit the questions that I would like to address in the future. But if we look just at this formula, I would say, you know, it makes sense, right? Because we are driving the electron very fast with the infrared pulse in few femtoseconds. And we are able to catch these changes of the absorption that they're related to somehow the energy dispersion on the baric structure. Now, the key question will be how to infer information about this, right? We can do models and say, well, you know, the model fits very well to the experiment. So that would be one possibility.
Well, you can get a lot of information about the energy dispersion from other experimental methods.
Yeah.
Okay, very, very interesting. Thank you. Okay, you should continue then.
Okay, so, but yeah, that's a very good questions. And then it comes back a little bit, what I wanted to show here is that, so far where we were is that to calculate this phase, so what we did is to plug in this phase, and this is just a semi-classical model. And then we calculate the absorption with the semi-classical model. And when we compare it with the numerics, we see that actually it compares very well. The fact that I have removed this part of the spectrum here is because in my model, remember that I didn't take into account the balance band. So I'm not able to understand what is happening around the K point, because this model is just to explain, for example, what happened in the M and gamma point. So these two features here. But we are not, with this model, we cannot grab what is happening around the Dirac points where you have promotion of carriers from the balance to the conduction. But if we look at the two of them, qualitatively, I think it looks really nice. And even if you look carefully to these patterns, you see that, for example, these have more asymmetric pattern with respect to the blue line, while this one, it has more an asymmetric pattern. So even the model is able to grab this. And we know that these are related with how is the energy dispersion around the K and gamma point. So if we look at the gamma point, it's more like a parabola, but around the M point, it's more like a saddle point. So we know that these patterns are kind of correlated with the local energy dispersion around these points. So this is why it looks symmetric or antisymmetric here. And finally, also, we try to thought about possible experiments in which maybe we can really emphasize more the part of the baric structure more than the energy dispersion. One possibility is to say, well, what we can do is an experiment in which we take a pan probe scheme, but instead of changing the time delay, what we are going to do is to change the polarization of the laser. So this is a linear polarization of the laser, and you're changing the the polarization. So first it goes from K to gamma, but then we are basically rotating the polarization. And then what we observe is that if we only take into account the energy dispersion, what we should see is that the transient changes due to these changes in the polarization should look like this, only if it's only energy dispersion related. It has the crystal symmetry as we were expecting. In the gamma point, they disappear because it's like a parabola, so we shouldn't expect any big changes here. So we see that that really is very different to when we have the very structure. So when we have the very structure, this second part, we observe that the absorption looks quite different compared with the one that we have only the energy dispersion. So of course, this calculation we did it only with the semi-classical model, but if we do the numerics and we compare it, this one with the numerics is just keep the same. And I'm reaching just the end of the talk. So just to say that now we have make good progress in the code. It's fully parallelized, and then we can use model 3D materials. So the first thing that we did, of course, is to do graphite. That is to add an additional layer and then put periodic boundary conditions. So what we did is to get graphite. We calculate the energy dispersion. We take only a few of these states, and then we calculate the absorption, and then we get very similar results to graphene. And the main conclusion is that it would be feasible with our code to really model this type of experiments. Just to give you a rough idea, for one time delay, more or less, it takes 11 hours by using 4 CPUs with 48 cores, sorry. And this for each time delay. So we have to do several time delays, mainly 60, 80 time delays in order to get this kind of Atta spectrum. And I think that with this, I wanted to finish, but just to say that we are also working including in the dynamics, the X and the exciton interactions. So the electron-hole interactions where we create these electron-hole pairs, they form these bound states. So we are working, towards extending the code also with electron-electron interactions. And I think that that's all what I wanted to explain. I hope that you like it. So if you have further questions.
Thank you. That was really interesting. People should be typing their questions into the chat, please. I'll start off. So the topological considerations, of course, change when you go from a single graphene sheet to 2 graphene sheet twisted, or graphene and then boron nitride, or what have you. Do you have any intuition about how that'll end up influencing that Berry phases term?
Yeah, this is actually something that we are working on, and so far we have not been very successful to get this information. I guess that the main idea will be if we are able to, with this technique, to characterize the topological phase of the material. So far we don't have a concluded result. I mean, it looks like yes, we'll be able to be able to say, for example, we have a topological phase or a non-trivial phase, but I think it's still too early to say.
Is there any work on straining graphene sheets to break symmetry and influence the topological character? That would be something that might be easier for your theory to handle.
So far, so far, what we can expect is that even for a two-band model, you can do like so you can do some models, and you can realize, for example, if you have a different topological phase, you would expect that the very curvature at different reciprocal, different, I would say, places of the reciprocal space will be different. So this is a little bit my hope that if this term is different, if we were on one side or the other side, and then we change the phase, and there is, you know, some changes here, that will be, you know, the only way to really track this. The main problem is that this part, the energy dispersion is strong, is actually the stronger always.
I see.
Maybe we have to come up with ideas like this one, right? In order to kind of emphasize what is the role of this part.
I
So,
understand.
but this is the main difficulty, is this one. But here, if the material change, there are models to really track how are the changes depending on the topology.
Mm-hmm. I understand. I apologize, a very basic experimental question. The attosecond X-rays, they're unpolarized, is that right?
They are polarized, and then but you can also have circular polarization. Yeah.
Okay. All right. Very very
both,
interesting. Yeah. Okay. Not seeing other questions right now. Then I'll thank you, Antonio. That was fascinating. Yeah, your research group is going to have a lot of fun as 2D materials continue to proliferate.
Yeah, you know, it's we're having fun. So,
how large does the device or the sample have to be? And I'll stop the recording now, and we can all just talk.